Hello, AP Statistics students. We are going to walk through this quiz on sampling distributions. There are some finer points in here that I think every one of you needs to be aware of, having graded these. I think, we may just have to reiterate these things in a conversation, but I want to walk through it item by item here. So, all right. The information I'm giving you to start about the human pregnancies, that it's a normal model with mean 266 and standard deviation 16. That's what we called, when we talked about this the first time, we called that the parent distribution. Meaning, and let's suppose it is approximately normal, meaning that this normal pile of data points, if I randomly sample one of these data points out of this pile, that data point is going to represent a single human pregnancy. It's going to be the length of it in days, right? So I pull one thing out and say it's 272 days. That's one observation in this pile. So that's the parent distribution. It's not the sampling distribution. And that's what we're referring to here. So when we say, how much is from 270 to 280, and I saw a lot of people draw the picture and say, okay, well maybe here's 270 and here's 280. And so we're just asking, what is this area? So this is just a simple, semester one type of question where you just need the z-scores. And you would say, all right, I've got 270 minus 266 over the standard deviation of 16. I've got 280 minus 266 over the standard deviation of 16. And that gives you a z-score here and a z-score there. So that would be, well, that's 4 over 16, so that's 0.25. And that's 14 over 16, so what is that? Oh, that's 7/8, so that's 0.875. So those are your z-scores, and I can ask the TI distribution, normal CDF. So now I know this area here is 21.05% of the whole thing. Alrighty then. So that's the percentage that we're looking for here in this question. At least how many days should the longest 25% of all pregnancies last? So we're again looking at the same picture, but now we want the longest 25%. Okay, so we're talking about somewhere, if we shade from there on out, we'll capture 25% of the distribution. So we want to know what z-score is that. So now we either go to the table and we look it up, but the other thing you can do is you can go to distribution, inverse norm, and you could put in 25. Notice that gives you a negative z-score because that's giving you, if I were to draw the symmetric line over here and shade that in, it would be the left-hand 25%, right? I want the right-hand 25%, which means I could just say, well, it's going to be positive 0.644. In fact, if I do inverse norm of 75, see, it's the same thing. 75% means I'm talking about everything up to here. The left, if that's 25%, the rest is 75%. So I just found z is 0.67449. That's more than enough place values. So now I'm saying, okay, the center is 266, standard deviation is 16. If z-score is this, then what is that actual length of that actual pregnancy? So I can say, well, the length of that pregnancy, x, minus 266 divided by 16 is equal to my z-score, which I know. So I'm just doing the simple algebra to solve that. I'm going to multiply by 16, add 266, and that will give me x. So I still have the number here. Multiply by 16, add 266. That's the length of that pregnancy. And we can, of course, round that to the, the integer number of days. So how many days should it last? Well, we could say at least 277, at least 277 days. And I better put the units, and actually, well, that's good enough. Okay, now, finally we get to the idea of a sampling distribution. So look, 60 pregnant women, that's our N right here. N equals 60, so we're sampling 60 and averaging them, and our Y bar here is the average of a particular sample of 60. Okay, so what does the distribution of that sample mean? So now we have another pile which is approximately normal, but this time, right, here if I pull one of those dots out, that's the length of one pregnancy. Here, if I pull out a dot, I get a Y bar, which is an average of 60 pregnancies. So every single one of these dots essentially represents 60 pregnancy lengths that have been averaged together to make a single number that then joins into this pile, this this hill-shaped pile. Okay, so that's what we mean by the sampling distribution. So the center of the sampling distribution is also 266, just like the parent was. But the standard deviation is going to be less. So it's asking, what's the distribution? So the model is, excuse me, approximately normal. The mean of the average of the sample means equals 266. That's the center. The standard deviation of the sample means equals this one. That's the standard deviation of the parent function, 16 divided by the square root of n. So that is okay. So oh, you didn't see when I was doing that. 2.066, we'll say. 2.066. Okay. Now I can answer questions like, what's the probability that the mean duration of these 60 patients' pregnancies will be less than 260 days? I want to know what is this area if that's 260. Okay, so I've got a Y bar, I'm pulling it out of there. What's the probability it comes from out of there? So then I can say, all right, well, I've got my z-score equals 260 minus 266 over not 16 but 2.066. Smaller denominator, more extreme z-score, less likely to happen. See, it's less likely to get an unusual average of the 60 than it is to get an unusual signal pregnancy length. So that's going to be -6 over this. So -6 divided by my previous answer is this. So it's approximately -2.9. Okay, and so I can just say, okay, well, that means that this is actually way down here, and I'm going to go to find that probability, I'll go to normal CDF, and I'll go from -100 to my previous answer of -2.9, yada yada, and I get like a 0.18, I can say, okay, well, probability that z is less than -2.9 equals 0.00184. There we go. Okay, guys, getting there. All right, now, original assumption, duration of human pregnancies can be described by a normal model is actually probably not true. In fact, it's most likely skewed to the left. Why do you think this is? A couple of you had a good thing to say here, and that was, okay, well, plenty of women have premature deliveries, but it's very unlikely for the delivery to be just as delayed as it could be premature. In other words, maybe your baby is born 2 months early, but it's not going to be born 2 months late. So that means that you have this distribution that climbs probably steeper than that. I mean, it's unusual to have all these babies born so early, but definitely it's going to crash right after 9 months, and that's going to be a skew to the left. Now, if it is actually skewed to the left, how does that affect the answers to the other questions on the quiz? So nobody really got my drift on this question. What I'm saying is, would we go back and change anything out of these answers with this knowledge? Now your answer should have been this. Well, we would probably need to change these answers because here we were assuming that we had a normal model. And so based on that assumption, we used norm CDF in the calculator to calculate this answer and to calculate this answer. And you know, we can't do that if it's not a normal model. We don't know if it's skewed. We don't know what the percents are. That's some other chart, and maybe no chart exists for the particular thing that we have. So these answers, maybe we just wouldn't be able to answer these questions at all. However, and you would have to go, you have to say, all right, well, for the parent function stuff, that would all be maybe unanswerable. But for the sampling distribution stuff, the answers would be the same. Even if this were skewed, even if we said wrong, it's actually skewed to the left. Okay, fine. Nevertheless, we would still get that same picture. We would still have an approximately normal distribution for a sample size of 60. If we were averaging them together, we would still see this picture, and we would still be able to answer this question the same way. And it would be an approximation, but we were already approximating. So we will say, this is still my approximate answer, okay? Because of the central limit theorem, so I can say, because of the central limit theorem, whoops, misspelled theorem, theorem. Because of the central limit theorem, the answers about the sampling distribution would be the same. That would still be approximately normal. That's the idea. Okay. All right, finally, guys, just before a referendum on a school budget, a local newspaper polls 400 voters in an attempt to predict whether the budget will pass. Suppose the budget actually has a support of 52%. What's the probability? Okay, now, we did this together in the group. You could either do it with p hats or you can do it with just x's. I'm going to do it with p hats just because we're trying to get used to using p hats. So let's say the budget actually has a support of, okay, so that's our p. Right, so the p hats are going to average, the average of the p hats is going to be equal to p. That's just going to be, and maybe I should have written that a different way, maybe expected value, but I'll keep it like that. And the standard deviation of the p hats is going to equal the square root of p times q over n. And n in this case is the 400 voters. Whoops. And the square root of that is 20, the denominator. So let's see, what is this overall? We have this, whoops. There we go. And then divided by 400, and then square root, so 0.0025, let's say. Okay, so the question is, what's the probability? Well, okay, we'll see defeat. Well, these p hats are distributed normally for sure. The center is 52%, or I'll say 0.52. And the standard deviation is this. Now, to predict defeat, well, if I predict 52%, that's not defeat. Defeat is less than 50%. So 50% is down here somewhere, and I'm asking for this area. It's the same kind of question, guys. Approximately normal model. I've got the mean. I've got the standard deviation. I've got a particular x value. I want to know a probability of the area under the curve for this section. Same thing. So I need a z-score. I divide this difference by my standard deviation. So I have 0.5 minus 0.52. I divide that by 0.0025. That is -8 on the nose. So my z-score is -8. Now, basically, guys, to the left of -8 is almost nothing that is, that we would acknowledge, right? I mean, and if I try putting that in here, whoops, that's where I want to be. Okay, so I could say from -100 to -8. I get a probability of 0, an area of 0. Now, it's not literally 0, but the calculator can only store so many place values. It simply will not report anything because this is beyond the scope of what the calculator is willing to report, or not willing. It has no will of its own, but it does not have the capability. It has not been designed to do it. So here's what we can say. We can say the probability that z is less than -8 is approximately 0, and we'll say it is negligible. Did I spell that right? Negligible. Okay, and so we can say it's so close to 0 that this is something that just would not happen. All right, see you guys soon.